All right, let's continue on with the solution process. So what happens when you actually take a solute like sodium chloride or sucrose or whatever the case may be and put it in water? Let's start off with and focus on ionic solutes such as sodium chloride. When ionic solutes dissolve in water, the water pulls the ions apart from one another in a process called dissociation. So the ions separate or dissociate from one another. So it's actually the water molecules grab onto the ions. So the water molecules, being polar, are attracted to the ions. And as a result, each ion then is surrounded by the oppositely charged end of a water molecule. That is, of course, if the solution is an aqueous solution. This process where the solvent particles surround the solute particles is called solvation. And if you have an aqueous solution where the solvent is water, then the process is called hydration. Take a look on page 500. There's a good diagram in there that shows sodium chloride. We have a crystal of sodium chloride, water molecules that are pulling those ions apart from each other. And then the green, I guess that's green, greenish blue, whatever you want to call that, teal, I guess. Chloride ions, notice that they're surrounded by the positively charged end of a water molecule. So if you recall, water is polar, and the oxygen end of the water molecule is partially negative, and the hydrogen end is partially positive. And so that partially positive and the hydrogen ends of the water molecules surround the chloride ions. We see the gray or silver color, those are the sodium ions, positively charged sodium ions. And so, of course, then the negative ends of the water molecules, oxygen ends, which is kind of like the orangish red color there, surrounds that positive ion. So that's what that means. Let me show you something else too so we can understand what actually happens when a solute dissolves. I have a simulation again here, so let's see if I can do this. Shake some sodium chloride out of here. Let's see. All right, so notice that before the sodium chloride hits the water, the sodium ions and chloride ions are all stuck together. So you have ionic bonds holding those together. And then when they hit the water, what's going to happen is the water molecules separates those ions from one another. So let's go ahead and do this. Let's let it go for a little bit. Now let me pause it. And let's count up the number of sodium ions. So sodium's kind of the pink color, chloride is the green. So how many sodium ions do you see there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks like there are 81, 82 sodium ions. All right, count the chloride ions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it looks like there's 82 chloride ions. So we see that there's one sodium ion for every one chloride ion. This will be important later on. So again, just click play again. So we have all this stuff moving around. You have these charged particles that are surrounded by water molecules. We can't actually see that in this case, but there are water molecules surrounding each of those ions. Those ions are moving around in the solution. A solution that contains charged particles, aka ions, are able to conduct electricity and are called electrolytic solutions. We'll see that on the next slide. So just wanted to point that out here. So there we have the spelling. Anytime you have mobile charged particles, such as the valence electrons in a metal that are delocalized, or in this case, mobile ions that are able to move around in a solution, that means it'll be able to conduct electricity. Not all substances, when you put them in water, will dissolve. If a substance does not dissolve, it most certainly will not dissociate. So how do you know if something will dissolve? If an ionic substance will dissolve, say in water, solubility rules. So back to the solubility rules. So let's do this little review of dissociation equations. Let's write the balanced dissociation equation for each of the examples in D. So we'll do magnesium chloride, we'll do potassium nitrates, and we'll do potassium sulfate. So recall that when you write a dissociation equation, it's not a chemical reaction that occurs, first of all. Second of all, we don't include the water in the equations. Let me just do the first one for you. You can do the other ones on your own. So what we're trying to show here is what happens when you put that soluble compound in water. So it's going to dissociate. So it's going to break apart into magnesium ions, a charge of +2, and chloride ions, which have a charge of -1. Make sure that your equation is balanced. All right, let me show you something first before you do those other two examples. All right, so let's go ahead and show what happens with something, say, like magnesium chloride. So I've adjusted here, up here, charge of the cation +2, charge of the anion -1. The magnesium ions will be black, the chloride ions will be white. So let's shake some of this out. Pause. I don't want to play yet. So again, notice all the ions are stuck together. All right, let's see what happens. So let's go ahead and pause this. And just by looking, it looks like there's more whites than black. So again, black is the magnesium ions. Let's count those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 45, 46, 47. 47 of those. And let's count the white, white representing chloride ions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 93, 94, 94. So we have 47 magnesium ions and 94 chloride ions. So what do you notice? Not only are there just more chloride ions, there are twice as many chloride ions as magnesium ions. And isn't that what this equation shows? When 1 mole of magnesium chloride dissolves, you produce 1 mole of magnesium ions and 2 moles of chloride ions. So make sure you understand the relationship between those two. All right, go ahead and pause the video. Writes the balanced dissociation equations for potassium nitrate and potassium sulfate. Pause now. So there we have it. Balanced dissociation equations for those two substances. And states of matter are included there. All right, letter G, let's do this. Let's go ahead and draw a picture of that magnesium chloride solution. So got some container, got some liquid in it. 1, 2, 3, 4, 5, 6. So that's our, say, magnesium ions. If there are 6 of those, then there's got to be 1, 2, 3, 3. Oops. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those, which are the chloride ions. So again, just showing that we have a ratio 2-to-1 chloride ions to magnesium ions in this solution. Very, very, very important for what we will be doing next. All right, in the last section, we calculated the concentration or molarity of a magnesium chloride solution. This time we want to determine the concentration of each ion, concentration of the magnesium ions in the solution, concentration of the chloride ions in the solution. So again, I'm going to go to my balanced, whoops, let's rewrite that, balanced dissociation equation, just so we can see again what is going on here. All right, so the concentration of the magnesium chloride, the solution as a whole, was 1.07 molar. We calculated that the other day. So now we're going to use this along with the mole ratio from the dissociation equation to determine the concentration of each of the ions in this solution. So let's do that. So start off with 1.07 molar magnesium chloride. And I'm going to write a mole ratio. We have 1 magnesium ion produced in solution for every 1 magnesium chloride that dissolves. Therefore, the concentration of the magnesium ions in solution is 1.07 molar. All right, let's do the same thing for chloride. Again, start off with the concentration of the solution as a whole. This time, according to our dissociation equation, 2 chloride ions produced for every 1 magnesium chloride that dissolves. And so this time we end up with this. The concentration of chloride ions in the solution is 2.14 molar. All right, second example that we did was we calculated concentration of the potassium nitrate solution, and the concentration of the solution as a whole was 0.892 molar. So go ahead and calculate the concentrations of both the K plus and NO3 minus ions using the same approach that I used in letter B. Go ahead and pause the video now. Show the work. Hopefully you showed the work. Remember that a formula in brackets means concentration or molarity. So the concentration of the K plus ions in the solution, 0.892 molar. Concentration of nitrate ions, 0.892 molar. We have a 1-to-1 ratio of those ions in solution, as we can see here from our dissociation equation. All right, I believe we have one more. So the third example, we had a solution of potassium sulfate, and the concentration of that solution as a whole was 0.0030 molar. So calculate the concentrations of the potassium ions in that solution and the sulfate ions. Go ahead and pause and do that now. Going back to our balanced dissociation equation for potassium sulfates, we see there's 2 moles of potassium ions for every 1 mole of potassium sulfate that dissolves, 1 mole of sulfate ions for every 1 mole of potassium sulfate that dissolves. And again, I did not show the work, but you need to show the work. Concentration of potassium ions is 0.0060 molar, and concentration of the sulfate ions is 0.0030 molar. All right, that concludes this lesson. Thanks for watching.